Okay, so what I want to continue with today is integrating without integration, or integration without integrating, whichever way you want to phrase this. You should be masters at the standard techniques of integration. You're integrating by parts, use substitution. You should be masters at the change of variable formula from Calc 3. You should know all the different ways. If you want to convert from Cartesian to spherical, you should have the stuff mastered. I am, for the most part, not going to use this in this class. What I want to do is I want to show you ways around this that really fundamentally highlight what's going on. A probability distribution is non-negative and it integrates to 1. Because of that, we have an enormous amount of things we can do. We can get essentially for free the volume and the surface area of the n-dimensional sphere. What I want to do is I want to talk a little bit about the gamma function. I'm going to then go from the gamma function to chi-squared random variables, which are going to be connected to normal random variables, and then just show a lot of these connections. All right, so the first thing is the gamma function. So it's defined as gamma of s is the integral x goes from 0 to infinity of e to the negative x, x to the s minus 1 dx, or sometimes it's written as the integral x goes from 0 to infinity, e to the minus x, x to the s dx over x. So again, as mathematicians, we can define almost anything we want. Most definitions are useless. When you see something like this, the s minus 1 should be a bit surprising. Why would we ever define this as s minus 1? When you're looking at this definition, you should just define that as an s. The reason is you should view the s minus 1 as it's x to the s and then dx divided by x. Where have we seen dx divided by x before? I'm sorry? Convolutions of products. When we had convolutions of two non-negative random variables, it wasn't just the naive collapse from the convolution of sums. We unfortunately had this factor of 1 over x coming from the chain rule. Instead of having z minus x, we had z over x. The real measure going on here is not dx, but dx over x. If I multiply x by 5, dx over x is unchanged. It's 5 dx over 5x. Okay, that's really what's going on. We want to now calculate values. What do you think is the easiest value of s to take? 1. So if we take 1, we get gamma of 1 is the integral from 0 to infinity of e to the minus x dx. This is an exponential random variable with parameter 1. When you do the integration, integrate by parts, you just get 1. Building on our success, what should we do next? 2. All right, so we get gamma of 2 is the integral from 0 to infinity of e to the negative x, x dx. All right, when you see something like this, what's your first thought? How should we handle e to the negative x, x dx? Yeah, we basically know use substitution and integration by parts. So let's try use substitution. We have an x. We want the degree of x to go down. It makes sense to try, let's let u equal x, dv equal e to the negative x dx. V would become negative e to the minus x. And then du would be dx. So when you now do this as uv at 0 infinity minus the integral from 0 to infinity of v du, the u and the v, I have e to the 0, but it's multiplied by 0, so that doesn't contribute. When I put in infinity, e to the negative infinity beats infinity. So the uv term vanishes. And now I have negative, and negative becomes a positive. Oh, this is nice. This is just the integral from 0 to infinity of e to the minus x dx. What does that equal? 1. So gamma of n equals 1 for all n. Yes or no? What do you think? Gamma of 1 was 1, gamma of 2 of 1. By induction, gamma of n is 1. No. All right, what should we do? What should we do? General case. We could gather some more data. And just in the interest of time, Gamma of 1 was 1. Gamma of 2 was 1. Gamma of 3 is 2. Gamma of 4 is 6. Gamma of 5 is 24. Gamma of 6. Anybody want to guess? 120. What does the pattern look like? It looks like factorials. So let's prove this. So let's look at gamma of s plus 1. I apologize that we're using the letter s. This is the conventional notation for this problem. So this is going to be the integral x goes from 0 to infinity of e to the negative x, x to the s plus 1 minus 1 dx. Whenever we have something like this, we always want to make sure it exists and is well defined. So the dangers are we could be dividing by 0 when x equals 0, and it may not decay fast enough as x goes to infinity. Well, the decay at infinity is fine. We have exponential decay, and we have at best polynomial growth. So going off to infinity, it's fine. But as x gets really, really close to 0, what does e to the minus x look like? As x gets close to 0, e to the minus x looks like 1. So if this over here, if this exponent is negative 1 or even more negative, this is not going to be integrable. The function 1 over x is non-integrable. It blows up. The function 1 over x squared is non-integrable. It decays, it explodes too rapidly at 0. So just as a quick recall, like the integral x goes from 0 to epsilon of x to the minus r dx is equal to x to the minus r plus 1 over minus r plus 1 evaluated at 0 and epsilon. Well, at epsilon is no problem. Oh, I'm sorry, I probably want to do it the other way. Don't go from 0. Let's go from epsilon to 1. When I plug in an upper bound of 1, there's no problem. But as epsilon gets smaller and smaller and smaller, if r is greater than 1, this is going to be x to a negative power. So this would be like a 1 over epsilon, a 1 over epsilon squared, a 1 over epsilon cubed. This would blow up. So this blows up if r is greater than or equal to 1. So when we're integrating the function x to the negative r, it's essential that the negative r can't be too negative. If this is negative 1 or smaller, we're in trouble. If it's negative 0.999999994, that'll be integrable. Because when we add the 1, we'll have a positive exponent up here. Not by much, but we just need a little bit. So again, whenever you look at something like this, you always want to ask, when does this make sense? So when we're looking at this, we just need this exponent here to be greater than negative 1. Well, we've got an s plus 1 minus 1, so as long as s is positive, we're fine. S could even be a little bit negative, and we would be fine. All right, so we want to try to figure out what's going on. So let's integrate by parts again. U is going to be x to the s, the 1's cancel. dv is going to be e to the minus x dx. v is going to be minus e to the minus x. And du is going to be s x to the s minus 1. And you can begin to see the factorial coming out. When we're doing the integrating by parts, we have an s coming out over here. And so now we have the uv minus v du as before. So this is uv at 0 infinity minus the integral from 0 to infinity of v du. The boundary term vanishes again, and we're left with gamma of s plus 1. Negative and a negative is a positive. We can pull the s outside the integral, and we have s times the integral from 0 to infinity of e to the negative x, x to the s minus 1 dx. And what does that integral equal? Gamma of s. So we get s gamma of s. And now you can see why we're getting the factorial function. So if s equals n, an integer, we get gamma of n plus 1 is n factorial. So we'll say n is a non-negative integer. This is a little bit annoying, right? We've just shown that the gamma function is related to the factorial function. You know, gamma of n plus 1 is n factorial. What would you like gamma of n to be? It would be nice if it was n factorial. To rectify this horrible miscarriage of justice, some mathematicians have defined a new function. G of s is gamma of s plus 1. And now you have a new function, and now g of n will be n factorial. It turns out this is the more useful definition. And it's just unfortunate that it's shifted a little bit from the standard factorial function. Okay? This is remarkable. This is known as a functional equation. If you know its value at s plus 1, you know its value at s. You can propagate downward. So there's an extremely useful identity called, I think, the secant identity, or cosecant identity. That's right, because things don't match the way they should. The cosecant identity. I will not prove this in class. There's several proofs given in the book. Gamma of s, gamma of 1 minus s is pi over, I think it's sine pi s. Okay. So this allows us to understand, if we understand gamma of s, we can get gamma of 1 minus s from knowledge of the sine function. As an advanced remark, everything we're doing right now, you can generalize this for complex numbers as well. And you can define the factorial function not just at the integers, not just at the reals, but also at complex numbers. The whole point of the gamma function is it generalizes the factorial function. At the integers, it equals the factorial function, but it's defined elsewhere. Now you might ask, why would we want to generalize the factorial function? I'm not going to try to reorder, square root of 5 people. Right? There's a limit to what we can do. Okay? Can anybody give me a reason why we might want to generalize the factorial function to things that are not integer valued? Yes? Excellent. We can. Wait, so I want to hear exactly what you said.
If you're looking at continuous solution.
Okay, so why would we need the factorial function at non-integer values?
If it's continuous, you need to define it in between.
Right. There's what's the advantage of defining you're close?
So you can integrate over it?
Close. We want to be able to use tools from real analysis. If we have a function that's defined for all values of the parameter, all of a sudden continuity results are at our disposal. Differentiation results are at our disposal. We can use that to try to figure out how rapidly this function grows. So there's an enormous wealth of information, a number of tools available as soon as we have something that's continuous. Think back to differentiating parameters, differentiating identities. Even if we only cared about the value at specific integers, we needed to have a continuous spectrum so we could differentiate. When you look at this formula, any idea what's the nicest value of s to put in? I'm sorry? Why? Because they're the same. If you take s equals a half, this is beautiful. It yields gamma of 1/2 squared is pi divided by the sine of pi halves. What's the sine of pi halves? 1. So this is pi. Now if you look at gamma of 1/2, gamma of 1/2 is the integral from 0 to infinity of e to the minus x, x to the 1/2 minus 1 dx. This integrand is non-negative. So what can you tell me about this value, positive or negative? I'm sorry? Positive. So we know gamma of 1/2 squared is pi. So gamma of 1/2 is either root pi or negative root pi. Because this is a positive integrand, it has to be square root of pi. If you are willing to do something a tad illegal and say that, well, the gamma function is just the factorial function shifted by 1/2, then gamma of 1/2 should just be 1/2 minus 1 factorial, or negative 1/2 factorial is square root of pi. So the number of ways to arrange negative half of a person when order matters is the square root of pi. Do you think we will ever run into this in our lives? Actually, yes, right now. I see at least one person wearing a football shirt. Does anybody remember the old Saturday Night Live skits on Ditka? Where Ditka can do anything. If Ditka would have played the Bulls would actually score a negative number of points because Ditka's that great. Ditka could handle the factorials of negative 1/2 integer, no problem. Where do you think we're going to see negative 1/2 factorial? So let's look at moments of the Gaussian. Moments of a Gaussian. We start off with, let's integrate from 0 to infinity of e to the negative x squared over 2 dx. What did we have to prove this equals? Square root of 2 pi. Okay. Does this look like the gamma function? Gamma of s was integral from 0 to infinity e to the minus u, u to the s minus 1 du. I want to use a different variable. Does this look like this? Is it close? It's close. Let's see if we can make them match. Well, if I want to make them match, let's have the exponentials line up. So what should I choose u to be? I'm sorry? X squared over 2. And then as as x goes from 0 to infinity, u is going to go from 0 to infinity. Du, oh wonderful, the 2's are going to cancel. Life is good. It's going to be x dx. I unfortunately don't have an x dx, I just have a dx. All right, that's not a big deal. Replace them, yes?
Why are we looking from 0 to infinity for the...
Oh, sorry. Thank you. Excellent point. Remember to email me. The reason we're doing this is because if I were to go from negative infinity to infinity, if I plug in x equals negative infinity, what do I get for u? Infinity. And if I plug in positive infinity, what do I get? Infinity. I forgot to go through this step and say we have to say that this is double this, because if we tried to do the negative infinity to infinity, this substitution would break down. So thank you. So we want to double from 0 to infinity so that the change of variable works nicely. All right, du equals x dx. We have a dx, so let's solve for dx in terms of du. This is the same as dx is equal to x to the negative 1 du. Well, if x squared over 2 equals u, then 2u equals x squared. So this is going to equal 2u to the minus 1/2 du. Right? So now our integral becomes 2 integral u goes from 0 to infinity. E to the negative x squared over 2 becomes e to the negative u. And now the dx becomes 2u to the minus 1/2 du. We're almost there. We have a 2, and we have a 2 to the minus 1/2. What's 2 times 2 to the minus 1/2? 2 to the 1/2 was square root of 2. So we have a square root of 2. We have an integral u goes from 0 to infinity, e to the negative u. Now we have a u to the minus 1/2. The gamma function, I want to write things as u to the s minus 1. How can I write u to the negative 1/2 in the form of s minus 1? Half minus 1. The whole point is to try to figure out what is the best way to do the algebra. The difficult part in these problems is always, how do you write the algebra? What do you know? What's given? Well, because of how we've defined the gamma function, we want to write the exponential as u to the 1/2 minus 1 du. Ah, what is this integral now? Gamma 1/2. So we get square root of 2 gamma of 1/2. There is the normalization constant for the normal. And for what we've done over there, we haven't proved the cosecant identity. That's another way to get that this integral is equal to the square root of pi. Absolutely shocking result. The connections don't stop here. This is one of the reasons why the gamma function is so useful. We just calculated the normalization constant. After we calculate the normalization constant, what would we want to calculate next? The first moment. All right, first moment won't be too bad because it'll be 0. All the odd moments are 0. Let's calculate an even moment. If we wanted to calculate an even moment, all I would have to do is take this and shove in an x to the 2n. This is the advantage of being at the blackboard, right? I can just shove in an x to the 2n with no problem. And really, I can view this as x squared to the nth power. So now all that changes over here is I now have to remember I have an x to the 2n. Well, x squared equals u times 2. So x squared is 2u. So I would get a u to the n, 2 to the n. And so now the only thing that would change is over here, I would now have a 2 to the n plus a half. And then I would have an integral from 0 to infinity of e to the negative u. And then I would have a u to the n minus a half. So I'd write that as u to the n plus a half minus 1 du. So again, right now the algebra doesn't really matter. I just want you to get the general feeling as to how you would do this. The calculation is the same. I just have this extra factor. The dx, I've already figured out how it changes. The exponential, I already figured out how it changes. This just gives me an extra u. Well, if you look at our definition of our function, that just changes the value of s. And so now we get 2 to the n plus a half gamma. And now where do we evaluate gamma? N plus a half. We get all the moments of the standard normal through the gamma function. It's a nice change of variable. It would be wonderful if we didn't quite have that 1/2. This 1/2 is coming from the fact that there's got to be that square root of pi that comes into play. And so, there's a limit to how much algebra I want to throw at you right now, but I want you to see that we can actually interpret all the moments of the standard normal through this function. And if we understand the gamma function, we actually understand how the moments of the Gaussian grow. When we're trying to prove the central limit theorem, this is the key big result of the course. The way we're going to prove that sums of random variables, that their mean converges to being normally distributed, is we're going to be looking at the moments of the distribution. And there's these big results in complex analysis that say if things are nice, if the moments converge, then the distributions converge. This is not always the case. Remember, we saw Taylor series. We could have a function whose Taylor coefficients were all 0, but the function was not identically 0. It's because of that that real analysis is hard. It's because of that that probability is hard. We need a little bit more to control the convergence. In the first course, I'm not going to go into all those details. I'm going to try to give you enough of a sense, prove the central limit theorem in a couple of key places. And then if you want, I will give you a bunch of lectures in complex analysis that you could then listen to and actually see the proof. Or just come in at 10 o'clock, and we'll be doing the proofs very soon in complex. Okay. Any questions so far on what we've done here? Yes?
If you were to include the normalization constant, would any of those 1/2?
Well, the problem is the normalization constant we would have, if we were to write it as a gamma of 1/2, we would then want to do some kind of shift involving gamma of n plus 1/2 over gamma of n. What you can do is you can do a repeated, let's see if it was, oh, it's actually swiveling. We could do a repeated application of gamma of s plus 1 is s gamma of s. And as you keep pulling that, you'll get s, s minus 1, s minus 2, eventually down to a gamma of 1/2, which will cancel. And you'll see things that look a lot like a factorial, like a double factorial. As a nice exercise, you should prove that you get the double factorial. If you think about what's going on, you're starting off with n plus 1/2. So you'll have n plus 1/2, n minus 1/2, n minus 3/2, n minus 5/2, n minus 7/2. Those don't look like the integers in the double factorial. But if you multiply them by 2, n plus 1/2 becomes 2n plus 1. N minus 1/2 becomes 2n minus 1. And look at that, we've got a 2 to the n. We've got all those powers of 2 waiting to come in. So it's a really nice exercise. Go through and see that this will give you exactly the double factorial. Okay, so this is the beginning of wonders of the gamma function. Okay, any questions on the gamma function so far? Okay, what I want to do now is I want to talk about a distribution that's related to the gamma function. And so in some sense, we've already done that because the normal distribution is related to a gamma function. That's really where the normalization constant is coming from. What I want to do is I want to do chi-squared random variables. So chi-squared distribution. And so we'll say x is a chi-squared random variable that's a Greek chi with new degrees of freedom if the following is true. We want the density to be 1 over 2 to the nu halves gamma of nu halves e, okay, we write the x first, x to the nu halves minus 1 e to the negative x halves if x is greater than 0 and 0 otherwise. Okay? So if I'm claiming this is a probability distribution, you should be immediately thinking 2 facts. 2 facts must hold. What are those 2 facts?
Non-negative integrates the 1.
Which is the easier one to check? Non-negative. So everything will be fine. Now we just need to make sure that it integrates to something that equals 1. I'm not going to go through the details of the integration. You can see that this looks a lot like the gamma function. What is the difference between this and the gamma function? What's the biggest difference when you look at this to this?
X over 2.
Yeah, we have an x over 2 here, and we just have a negative view over there. So you'll have to do some kind of change of variables. Let u equal x halves. So change variables, u equals x halves, and then just do the algebra, do the integration. And you can see this looks a lot like a gamma function. This is going to become the exponential you need. Over here, this will become a u to the nu halves minus 1. Oh, that looks really nice. We'll have some powers of 2. That'll cancel the powers of 2 here. We integrate, we'll get a gamma of nu halves that will cancel with this. Okay? So you can do the calculation. You can prove that this is a random variable. It turns out that this is one of the most important random variables there are. How many of you have taken statistics? Excellent. What do we assume about our errors in statistics? Normally distributed. Later in the semester, I'm going to give a lecture on why we measure errors with squares. The reason we measure errors with squares is because the squaring function is differentiable, calculus is available. If we use absolute values to measure error, we can't use calculus. If we don't use absolute value at all, if we just look at the difference, well, then error is a signed quantity, and a positive error can cancel a negative error, which is really bad. We measure errors with squares. In statistics, we assume errors are normally distributed. So this leads to the natural question, what is the distribution of the square of a normal random variable? Any guesses as to the shape of the distribution of the square of a normal random variable? I'm sorry? Well, sums of normal is normal. Chi-squared. Why would you guess chi-squared? We're doing chi-squared right now. It's right on the board. It's what we were doing right before asking the question and having the segue. This is one of the reasons why chi-squared is so useful. If you want to if you want to discern the distribution of errors in measurements, you will often be assuming you are summing normally distributed errors if your theory is correct. And then the chi-squared distribution will tell you how likely you expect the error, the sum of these squares, to be a certain amount. And if it's much greater than that amount, then your theory is wrong. And this is why the chi-squared is so useful. So the question is, if x is normal, mean 0, variance 1, then what is the distribution of x squared? So this will allow us to review our methods. What's our fastest, cleanest, easiest method to calculate the density of a function of a random variable? What method do we like to use? The cumulative distribution method. Excellent. So let's let y equal x squared, and we'll use the CDF method. So this means the probability that big Y is less than or equal to y is just going to be the cumulative distribution function of y at y. This is going to be the probability that x squared is less than or equal to y. Okay. What does it mean for x squared to be less than or equal to y?
X should be less than the square root of x.
I'm sorry?
X is less than the square root of x.
Not square root of x.
Square root of y, sorry.
Almost.
Okay, you know x is positive.
We do not know that x is positive. X is normal 0, 1. So if we know that x squared is less than or equal to y, we get fy of y is equal to the probability that negative square root of y less than or equal to x less than or equal to square root of y. Okay, now we need to integrate the normal density. Do we care what the integral of the normal density is? What are we going to do as soon as we calculate the integral? Differentiate it. So there's no reason to write down what it is. We just get fy of y is the antiderivative, it's the cumulative distribution function at square root of y, minus the cumulative distribution function at okay. If you wanted to, you could also argue by symmetry and say that this is just twice the probability that 0 less than or equal to x less than or equal to square root of y. Because the density of the standard normal is symmetric, we can just go from 0 to square root of y and double it. If you don't see that, you could do it the longer way. If we did it this way, it would then be 2 fx of square root of y minus 2 f of 0. We actually know what fx of 0 is. What's the cumulative distribution function of the standard normal at 0? A half. Do we care? Do we care that it's a half? No, why don't we care? We're going to differentiate it in a moment. Yes, the value is a half, but we're going to differentiate it in 1 second, so it doesn't really matter. We don't have to write that it's 1/2. I prefer using this formula because I only have to use the chain rule once. If you don't feel comfortable, just do this and differentiate twice. So we now get the density of our function y is twice the derivative of the cumulative distribution function of x at square root of y. This is the chain rule times the derivative of square root of y. Well, the derivative of the antiderivative is the original function. So we get 2, our original function, the normal density, at square root of y. And now we have to take the derivative of y to the 1/2. Well, that's going to become 1/2 y to the negative 1/2. Okay? We know the density function of the standard normal. We now just substitute in. The 1/2 and the 2 cancel. And we will be left with 1 over square root of 2 pi e to the negative input squared, which is going to become a y over 2, y to the minus 1/2. Yes?
Why didn't you have the derivative like the 2 times the thing at 0?
I'm sorry?
Isn't there like another term like the -2?
Yes, but this is a constant.
Oh.
It actually equals 2 times 1/2, but it doesn't matter. It's a constant. It has no y dependence, so when we differentiate, it goes away. So whenever possible, I'm trying to simplify the algebra as much as I can. Okay? Does this look familiar? Looks a lot like a chi-squared distribution. We have an exponential. Now the argument is supposed to be a nu halves minus 1. So if we want to write this as a nu halves minus 1, we can write this as e to the negative y over 2, y to the 1/2 minus 1. Now 1 over square root of 2 pi, we can write this as 1 over 2 to the 1/2 gamma of 1/2. And this proves that a standard normal, if you square it, it has the chi-squared distribution. Okay? So this is a wonderful calculation. Again, we don't have to know the antiderivative. This is the power of the CDF method. You use it as a placeholder. And it allows us to get a closed form expression for the density of y in terms of the density of x. This also tells you now why, when we were defining the chi-squared distribution, we've defined it slightly differently than the gamma function. You always want to ask yourself, why are we making this definition? It's not to make your lives painful. That's a side benefit. Okay? The reason is which occurs. Okay? For a lot of things, the gamma function, that occurs naturally. It's good to have that as the definition. But when we're looking at sums of squares of normal random variables, it's the chi-square distribution like this, bless you, that comes into play. Yes?
Are we assuming there that the, I don't know, Greek letter that is the chi-square?
The nu, yes?
The nu?
Yes.
Are we assuming that's 1 there?
So it would be 1. So the standard normal, it's a chi-squared. And so the answer is, let me write it over here. So the answer is x squared is a chi-squared random variable with 1 degree of freedom. So we often call nu the degrees of freedom. Nu equals degrees of freedom. It's the name of the parameter. And so here, we're doing the special case of nu equals 1.
And how do we know there's 1 degree of freedom?
Well, just when we look at this calculation, when we want to write this density in the same shape like this, the nu equals 1/2 works. We get 1/2 minus 1 is negative 1/2. So this is just algebra to make this look like the definition of a chi-squared random variable. And when we do that algebra, it does come out to be nu equals 1. Yes?
So would nu take on different values if we're not on a standard normal?
So the thing, if we're not on a standard normal, if you have, the mean is not 0, and if you rescale the variance, things are bad. So you always adjust things to have mean 0, variance 1. And then the question becomes, what if we start summing a bunch of normal random variables? So let's do that as the next exercise. So the question is, we could spend easily a week doing questions like this. Do you want to do sums of squares of 2 normal variables, or do you want to just jump and do the sum of n?
Sum of 2.
Sum of 2? All right. So sum of 2 normals squared. So we'll have x1 and x2 are both normal with mean 0, variance 1. We'll look at x1 squared plus x2 squared. We'll call that y. And we want to look at what is the probability that big Y is less than or equal to little y. Every problem starts the same way. This will be the cumulative distribution function of y at y. And now geometrically, this is going to be the double integral over x1 squared plus x2 squared is less than or equal to y of the density function of x1 at x1, the density function of x2 at x2, dx1, dx2. because we're talking about all pairs. Y is x1 squared plus x2 squared. So what's the probability big Y is at most little y? It's the probability that I take a pair x and y, and the sum of their squares is at most y. Yes?
And they're independent?
And they're independent. Can anybody tell me what shape this is? It's a circle. What's the radius of the circle? Square root of y. We keep getting these square roots coming in again and again and again. So what was going on is if we actually substitute for what's going on, we have an integral x1 squared plus x2 squared is less than or equal to y. The densities, if we now combine the densities, we get a 1 over 2 pi e to the negative x1 squared over 2 e to the negative x2 squared over 2 dx1 dx2. When you see something like this, what do you want to do? Polar coordinates. And so if we want to shift this to polar coordinates, we then let x1 be, cosine theta. We let x2 be sine theta. So we switch to polar. And we get the cumulative distribution function of y at y is the integral, the radius goes from 0 to how much? Square root of y. And then we have theta goes from 0 to 2 pi. Something deep is probably going on. When you see pi, what should you be thinking about when you see pi? No, I mean, it would be wonderful if you think of the gamma function, but from your earlier days before college, when you see pi, what do you think of? Circles. It's nice that we finally see circles coming into play. We're shifting to polar coordinates, and the pi is coming in. There's a deep connection going on here. So now our function is 1 over 2 pi. Now we have e to the negative x1 squared over 2, e to the negative x2 squared over 2. This is e to the negative r squared over 2. Then dx1 dx2 becomes r dr d theta. I have to write it like that because I've got my theta written first. Can you do the theta integration? Yeah, theta integration is pretty nice. And it's going to cancel the 2 pi perfectly. And now we're left with fy of y is the integral r goes from 0 to square root of y e to the negative r squared over 2 r dr. Can you do this integral? Should we do this integral? We're about to differentiate, right? We're going to use the fundamental theorem of calculus. We're going to integrate this and evaluate it at square root of y and then subtract off its value at 0. And then we're going to immediately differentiate. So if you call this function g of r, big G will be its antiderivative. So we get capital Fy of square root of y is big G of square root of y minus big G of 0. So now if we take the derivative, we get the density function at square root of y is now g prime at square root of y times the derivative of square root of y. G prime is going to be just little g. And so we'll get g of square root of y, and then we'll have a 1/2 y to the minus 1/2. And using a definition of g, we will get an e to the negative y over 2 right. And then we also have a factor of r, which is going to be a square root of y times a 1/2 y to the minus 1/2. And so when the dust settles, you get 1/2 e to the minus y over 2. So this is the answer for the distribution of the sum of the squares of two normals. Yes?
And that step up there, why are you multiplying the density of x1 and the density of x2?
Well, because I'm just trying to calculate what's the probability that big Y is at most little y. So if you think of all the possible values, x1 and x2 are independent. Here's my x1, here's my x2. I want their sum of their squares to be at most y. So that means that I'm integrating over the plane of the values of x1 and x2 inside this circle of radius squared of y. So that's going to be my probability.
Okay, that makes sense.
And so when the dust settles, we get 1/2 e to the minus y over 2. It turns out this is a chi-squared random variable with 2 degrees of freedom. So that is where the miracle is happening. So if we summed one normal squared, we got a chi-squared with 1 degree of freedom. If we sum the squares of 2 normals, we get a chi-squared with 2 degrees of freedom. What do you think would happen if we had 3? 3. What if we had 4? It all follows very much the same. What would go on here is you would just have more and more exponentials, and you would have no angular, well, the angular dependence is going to be very nice. So I will do the angular dependence on Monday. What I want to do is I want to end with the sum of 2 chi-squared random variables. So we'll say x1 is chi-squared with new 1 degrees of freedom. x2 is chi-squared with new 2 degrees of freedom. And so if we're going to do this, we need to recall what the density of the chi-squared is. It's almost made it a whole class. So what we'll do is we'll say the density of x1 is some constant 1. We could actually write down what this constant is in terms of new 1 and new 2. I don't really care what the constant is. That's the whole point. I just care about the functional shape. And so for the chi-square distribution, it's going to be e, I just want to make sure I write this correctly, to the negative x1 over 2. And then it'll be x1 to the new 1 over 2 minus 1. The density of the second one, it has its own normalization constant, e to the negative x2 over 2, x2 to the new 2 over 2 minus 1. If we now let y be x1 plus x2 independent, then we can use our convolution results. And the density of y is going to be the integral t goes from what to what? Minus infinity to infinity, the density of the first one at t, and the density of the second one at y minus t dt. So now we want to figure out what should the range of integration be. Well, this density is 0 unless t is positive. So because of this factor here, where does t have to start? So this one forces t to be greater than or equal to 0. Now for this one, we can't integrate past y. Because if we went past y, then this would be evaluating at a negative value. So this forces t to be less than or equal to y. So we get our density function is the integral from 0, from t equals 0 to y of c1, c2. We'll get an e. Now we're going to plug in t. So we'll get a negative t over 2, t to the new 1 over 2 minus 1. Then the second one will be e to the negative y minus t over 2, y minus t new 2 over 2 minus 1 dt. All right, we're almost done. We can pull the two constants outside the integral. We have an e to the negative t over 2. We have an e to the negative t over 2. That cancels. We have an e to the negative y over 2 that we can pull out. And we're left with t goes from 0 to y of t to the new 1 over 2 minus 1. And then we have a y minus t to the new halves. Good luck with this integral, my friends. Right? This is not an integral you've seen in Calc 1 or 2. Do we need to evaluate this integral? Somewhat, because we're not taking a derivative anymore. This is the density. The convolution gives us the density. We only need to figure out the y dependence in this integral. We don't need to actually evaluate it. So t goes from 0 to y. Let's have a new variable. Let's let t equal u times y. U is going to go from 0 to 1. So this integral now is c1, c2, e to the negative y over 2. U goes from 0 to 1. T becomes uy, so we'll have a u to the new 1 over 2 minus 1, a y to the new 1 over 2 minus 1. Over here, y minus uy, we can pull out a y. We'll have a y to the new 2 over 2 minus 1. And then we'll be left with a 1 minus u to the new 2 over 2 minus 1. dt is equal to u dy. All the algebra is in the book. I'm just giving you the quick idea. We pull the y's outside the integrals, and we get c1, c2, e to the negative y over 2. What will we have over here? OK, so let's see. dt was y du, so this is a y, not a u. So we're going to get a y to the new halves over 2 minus 1, y to the new 2 over 2 minus 1, plus an extra y. So we'll get a y to the new 1 plus new 2 over 2 minus 1, some crappy integral. U goes from 0 to 1 of u to the new 1 over 2 minus 1, 1 minus u to the new 2 over 2 minus 1 du. Does this integral have any y dependence? Does this integral have any y dependence? It's a constant. Call it c. So we get c, c1, c2, e to the negative y over 2. I'm excited. Y to the new 1 plus new 2 over 2 minus 1. What density does this look like? Chi-squared with how many degrees of freedom? Because this is a density, it must integrate to 1. So this number here, it has to be whatever the normalization constant you need for a chi-squared random variable with new 1 plus new 2 degrees of freedom. I don't need to evaluate this integral directly. It has to be, yes?
How do you know it has to be a density?
I'm sorry?
How did you know that it has to be a density?
Because it's the convolution.
Okay.
Convolution has to integrate to 1. We've proved that. We can now use all of our great results. Yes?
If t equals uy and there's u's in there, aren't there y's in there then, in that integral?
So we're replacing all the t's with uys, and then we're pulling all the y's outside. What's nice is I can pull out the y's. I get uy to the blah. I can pull out the y to the new halves minus 1. Over here, I get y minus y times u. I can factor out a y and pull that out. It's only because I can pull the y's out and reduce this to an integral that depends only on u and not on y that the method works. This has to be a universal constant now. The constant is actually ratios of gamma functions. We don't need that. This is the whole power of the method. We can now show that the sum of two chi-squared random variables is a chi-squared random variable. By grouping, we can now do this for sums of 3 and 4. So we'll talk more about this on Monday. We will then go over Stirling's formula for estimating the rate of growth of the gamma function. Okay.